How does one atom actually recognize another? And why do some pairs snap together while others pass like strangers in the night? In the energy filament theory, atoms do not feel a mystical chemical affinity. They simply read each other through the slopes and rhythms of their outer textures. They only stay together when those textures sync in a way that makes life easier for the surrounding energy seas, instead of little balls parked in empty spaces. The outer layer of an atom is made of electron filament rings racing along specific orbits. Each orbit has its own beat, its own way of looping and pausing. So together they carved a directional, rhythmic field around the atom. It's like a tiny wind pattern with both shape and timing. That outer field is the atom's voice and business card. It announces to the universe, in texture language, "This is the way I like energy to move near me." When two atoms drift close, the first thing they really sense is not each other's weight. It's whether these outer rhythms can lock into a shared pattern. The circulating electrons leave spiral traces that form invisible grooves around the atoms, preferred lanes where another atom's texture can fall into steps. In some directions, the beats match easily. The slopes between them tilt towards each other and energy can flow with very little internal friction. It's like two dancers who hear the same song and find themselves moving in sync without even trying. In other directions, the beats are always a bit off. Every attempted step lands on the wrong count, and the safest outcome is for both partners to back away to their own corners. Hydrogen and oxygen are a textbook example of a natural match. Hydrogen's single electron path creates one simple, exposed groove that fits neatly into one of oxygen's outer texture channels. Their spiral rhythms are almost perfectly aligned, and from the energy sea's viewpoint, tying these two patterns together costs less tension than letting them wobble separately. So the system quietly slides them into a shared configuration that we label as a chemical bond, and later romanticized as water loves to form. Carbon takes this to another level. Its outer electrons sculpt four especially cooperative grooves that point toward four well-separated directions in space. It's like a tiny tetrahedral scaffold. So carbon can extend for hands into four different rhythm channels at once and shake hands with four neighboring atoms. It builds chains, rings and sheets with absurd ease. That's why almost every complex structure in biology ends up being some elaborately folded way of letting carbon keep those four beats in harmony with many partners. Helium, by contrast, walks into the ballroom with the doors already closed. Its outer electrons fill their available orbits in a way that wraps its texture back onto itself, forming a nearly perfect closed shell with no open grooves. It's like a small house that has pulled down every blind and latched every lock. So from the outside, there is almost nowhere for another atom's rhythm to hook in. When another atom approaches helium, it is not pushed away by some aggressive repulsive hand. It is simply never offered a place to step where its beating would feel comfortable. As a result, the easiest move for the energy sea is to leave helium and the visitors each resting in their own minimum tension states. This shows up to us as chemical inertness or noble behavior. You can imagine the whole periodic table as a crowded dance floor where each atom carries an invisible rhythm bubble. Some, like hydrogen, have very simple beats and quickly find partners. Some, like carbon, have versatile patterns that can sync with many different neighbors and build huge ensembles. Others, like helium and neon, are wearing headphones and happily dancing alone in their own heads. Whether two atoms have chemistry is nothing more than whether their outer textures can synchronize in a way that carves a downhill path between them. When their rhythms line up, the textured slopes tilt toward coming together and the atoms slide into a shared, low-effort configuration. When the rhythms clash, the slopes point toward separation and the atoms drift apart again. A chemical bond, in this language, is just the state where two atoms' outer fields have found a common, the route through the energy sea that is smoother than any route they can walk alone. So the universe simply lets them stay that way. Tap follow, share it on New Physics, Clear Universe.